Welcome to RCast, the official podcast of the RChain Cooperative. RChain is a complete concurrent blockchain platform designed for maximum efficiency at minimal computational and environmental costs by utilizing proof of stake. I'm Derek Barris, the director of content for RChain. We cover a range of topics on this podcast, from the foundations of blockchain in general to the specifics of RChain, including our foundational language, Golang, as well as issues in calculus, governance, security, and the forthcoming businesses and dApp development on our platform. Please check out rchain.coop to learn more about our platform, as well as information on becoming a co-op member.
I would like to talk about some work that began in 2017 when I observed that there's a derivative at play when you do the reflective closure. And recently, Mike and I have been looking at that work in a new light, which is, well, initially, I mean, what I've been thinking about was once you have this observation that the reflective closure behaves in a derivative-like fashion, then could you focus just on rewrite rules that use reflection and reification? And that turns out to be sufficient to capture all of the rewrite rules for all the sort of complete notions of computation that we know about. But it's not necessary. And that's okay. We don't need to be necessary and sufficient. We're just interested in a rewrite format that is sufficiently expressive, that we could restrict attention to that and then insist that if you were going to give us other rewrite formats, that you gave us an encoding in that presentation. So that's a lot to take in already. Let me stop and check in and see if that all makes sense.
Yeah, I was going to ask, could you say a few words about just what you mean by reflective closure?
Yeah. So it turns out that you can take if you're given a parametric type, let's say T is parametric in X, then you could form the type R, which is equal to T of R. That closes up the variable.
Okay, so kind of in like a fixed point manner?
Yeah, it's a fixed point manner. Yeah, exactly.
Okay, cool.
Yeah. Let's begin formally and then work our way out to the meaning of it and why this is relevant and important. On my screen, I'm assuming that I've got this polynomial functor that's parametric in some collection of constants ki, or bold k is the entire collection, and ki indexes over that collection, and some variable x. So for the ith power of x, we have the ith tag or constant. So that should be pretty straightforward. Nothing fancy there. It's not quite as rich as a Leverrier theory, not quite as rich as a species, but it's a polynomial functor. Now we can take a formal derivative with respect to x. Basically, it works just like the derivative. You lower you're punching a hole in every place where x could occur, and so at the ith position, it could occur in the first position, or the second position, yada yada yada. So you get I minus one of those. So it looks just like a derivative. And then to fill the hole that we just punched in the data type, we take the product with something. Whatever it is we want to fill the hole with, we're going to take the product with that. So in this case, we're going to take the product with some type that's parametric in k and x. And we're calling it n. N stands for name, and you'll see how names arise in a minute. But essentially, by taking a product with names, we're filling the hole that we just punched in the data type with the named type. And I've sort of spelled out that calculation, right? So if we say t prime is the derivative of t with respect to x cross n, then you can distribute that through all the components of the sum that t is. And so that means that where you just lost an x component, you're replacing that x component with a name. Does that make sense? You're following the calculation so far?
Yeah.
Go ahead.
K is a sequence of natural numbers.
K is a bunch of tags. It's indexed by natural numbers. Think of it as term constructors.
And each ki is the set of tags of I-array operations.
That's right.
And then you're poking a hole, but it's still an I-array operation, and we want to fill that hole with a name that's clear.
That's right. That's exactly it. Now we've got names filling the holes, and since we've got names, we want name management technology. Lambda is the best name management technology, but we're going to do an impoverished form of Lambda. And this is because we're only going to allow you abstract over names, but you can only apply an abstraction to a name. And that's because we allow names to be dropped, dereferenced. So at some point, someone's going to tell us how a name is related to a term. If we're given that magic, then we could dereference a name to a term. And that's what the first term in this Lambda data type is. And then the second one is an abstraction. The third one is an application of an abstraction to a name. And then we ground these out. These are like built-in types for a Lambda calculus. So they can either be a context or they can be a term. So completely filled in.
Okay, and these contexts are the derivatives that you were talking about before, right?
That's correct. That's exactly right. Well, it's a derivative. It's a derivative with a hole in it. That's a name.
So why are we only applying a term with a distinguished name to another name? Couldn't
Because we can drop names. We get the equivalent of higher order capability because every name can be dereferenced to a term.
Okay. Yeah. And where are we seeing that dereferencing here?
Yes, that's the first term in the Lambda data.
Yeah.
Now, as promised, we say that a name is really just a decorated term, which is saying that names are freezing computations. And then finally, we take the fixed point with respect to X. And that's the data type that we can derive. And we do this. So notice the important thing is that we don't do any fixed point calculations until the very end. Basically, if you're familiar with Haskell type shenanigans, we remain sort of at the two-level type decomposition. We don't do any recursion that we don't have to. So Lambda is recursive because it mentions, but the T is not recursive, right? So when a T could become recursive and become a term type at some point, but at the top of the calculation, it's basically like a scaffold. And you could build a term calculus out of it, but it's really just a skeleton of a term calculus. And then step by step, we sort of fill in that skeleton with pieces that will be necessary in order to do calculations, computations in particular. And then at the very, very end, we close everything up. This gives us a kind of decomposition of each of the features that we need to add to our language. All right, so we start off with some built-in calculations, which are the operations indicated by the KI constructions. So those are term constructors for some built-in notion of computation. And then we make contexts out of those things. And then we fill those contexts with names. Then we provide name management technology, which is the Lambda, and we provide the weakest form of name management technology. So it's weaker than Lambda calculus.
What do you mean by name management?
The way I think about Lambda, it took me some years to come to this, but if you have some kind of namespace construction, or namespace that you need to be able to do computations on, Lambda is your best bet. It's the simplest way to have abstractions and fill those abstractions. There's this substitution of values for variables. That's Lambda's only job.
Yeah.
Right. And so that's what I mean by name management technology. I want to be able to just make abstractions and then boil them away through application.
This is distinct from the abstraction analog in the row calculus, which is input.
No, what we'll find is that we recover all of that with this.
Okay.
Once I show you, it's easy to recover the row calculus. But notice that we now do this for any term calculus, right? So this, at a minimum, this would give you row with a set of built-in operations, where the built-in operations are T, given by T. And the other piece is that all of this is completely generic. There's nothing special about this. The only thing that we insist on is ultimately, and I for this talk, I've made T be very tame. But ultimately, it just has to be differentiable. I have to be able to poke a hole in it. So it can be a pretty sophisticated functor as long as I can poke a hole in it. And then fill the hole with names, and then do abstraction over names, and then provide the reflection of names, of terms as names, and then finally do the fixed point calculation. I keep hammering this point out because it's really important to understand how generic this is. You might be interested in this, Christian, since you're interested in adding reflection to Fiore's program.
Yeah.
So I think this at least should give you a foothold.
Yeah, definitely.
Yeah. Let's look at an example. Well, first, notice that this gives us reify. So the at map will give you a lambda kx to an n kx. Sorry, there's a typo in the slide, but it's lambda kx to an n kx. And reflect gives you a special, if you have an application, then you can get a tx out of it. But if you don't have an application, then all bets are off. So that's a partial function. In general, you want to at least respect that at star at of t is equal to at of t. Now, in the case of row lang, as opposed to the row calculus, you have that at and star inverses of each other. So the t you're taking care of is literally being frozen. So when you say, give me the address of t, that address can be used to retrieve a t that is structurally equivalent to t and not just t-ish. If it's t-ish, you can't even demand they're bisimilar because that ends up being halting hard. But as long as you get it on the nose, exactly inverse, then you can obviously, by demonstration with Rolang, you can get a solution to that equation. So there's two different equations here. One is a special case of the other. Therefore, when you form an abstraction, the abstraction of n over star of n applied to at t should be t. Right? It should reduce to t.
Yeah, that's reminds me of the semantic substitution from row calculus.
Yeah, that's exactly right. That's the semantic substitution of row calculus. So these two equations are giving us enough to recover row calculus. So we're giving like a very abstract account of row calculus. If I've got k tags for, out, and par, then you can see for yourself that I can form a term that looks like this. So that's how I can do a red X. And then obviously I can now make a rewrite rule that's exactly the for rewrite rule. And again, I'm just using lambda n dot t as short for the abs in t term in that data type. That makes sense, Christian?
In generality, like how are we deriving the reify and reflect maps from the functors?
That equation tells you how to do reify. You hand me a t, I just pair it with at and
Yeah.
Yeah,
right.
reify is just quote, basically, right?
That's right. That's exactly what it is.
Okay.
That's correct.
Yeah.
And then reflect is partial, right? It only works if you've got one of the application gadgets. If you don't have an application gadget, we say bottom, we fail.
What we're doing doesn't apply to like any polynomial functor. It needs to be of a certain form.
No, the whole thing works for any polynomial functor. It's just that
You might get bottom.
you might get bottom for lambda. If you give me a lambda term that is an abstraction, I can't auto-generate, from an abstraction a term,
Mm-hmm.
right? Unless you say that the abstraction is a term. If you go from lambda to lambda, as opposed to lambda to t, you can get what you want.
Mm-hmm.
So now we can build row calculus out of this formulation. And we can build a reflective variant of the lambda calculus. And we can do lots and lots of things with this gadget, right? There's literally an infinite number of rewrite systems that we can capture with this formulation.
Yeah, this is really cool. So you're basically just providing a framework, and then you can put whatever term constructors you want in there as those K sub i's, and
That's right.
generate any reflective calculus, I guess, built from those term constructors, right?
That's exactly right.
Yeah, that's super cool.
So one calculus that's out of reach directly is the ambient calculus, because the ambient calculus doesn't work by substitution.
Mm.
It works by whole tree rewrite.
Okay.
So you have to go through an extra step. You basically have to turn every ambient calculus thing into some data, and then do pattern matching on the data with your substitution machinery, and then reflect it back into your term. So one Christmas I gave a talk on how all that works. You can't make ambient fit this pattern directly. You have to go one level of indirection in order to get there. But in general, we can do all the computational calculi in this style. Now, the reason I'm interested in this goes back to Ladle. Essentially, in the last few months, Mike and I have been investigating what the relationship is between the Kairos style types and the session types, and I'll focus on the Abramsky formulation of the session types as opposed to the way Wadler does it. Because Abramsky's formulation is very crisp and clearly laid out in terms of realizability. And that realizability construction allows one to see that the effective distinction between session types and the Kairos style types is the relationship between the negation and execution. If you remember, when we're talking about Ladle, what's interesting is we formulate it in terms of some components, right? So you need a monad for your collection, you need a monad for your term calculus, and then you need your distributive law. And in the case of the Kairos types, the negation is coming from the collection. In the case of sets, right, you've effectively got a Boolean gadget. And so it has a crisp notion of reflection in terms of the Boolean machinery. In the case of the Abramsky types, the negation is coming from the evolution. So it's coming from the term language and its rewrites. The slogan, or the way to think about Abramsky's characterization, is he takes the Girard quantale. So for listeners who are not familiar with linear logic, there's a particular semantics. So all models of linear logic are some form of quantale. And a quantale, it can be given as a presentation of every quantale can be factored through sets of sequences. You have some initial set of generators. You consider all the sequences of those generators, so that's a monoid construction. And then you consider sets of those sequences. And then every model of linear logic factors through one of those gadgets. The free one will look like that. Something that's more constrained will have some equations on it. That's kind of a piece of folklore about linear logic. And then the Girard quantale is effectively spelling out how you take that free gadget and then add in the linear negation. So to add the linear negation in, you have some thing which is what's called a dualizer. If the generators that you started with are actions, then the dualizer says what undoes or screws up those actions, what's in conflict with those actions. To negate, for each thing in a set of sequences, you take the things that screw them up, and then you're looking only at the double closed sets. When I take whatever screws up my set of sequences, and then I take whatever screws that up, I should get back to the original set. And so the double closed construction is effectively the Girard quantale. And what Abramsky does is he splits that so that the actions are not the generators, but we understand that the actions are evolutions of the rewrite rule.
What are these conflicts between actions?
This is just given. It's part of data that you give.
Okay.
That's what the dualizer is.
Yeah.
And so Abramsky sort of he kind of splits that into the rewrites, right? So he relates the notion of action to the rewrites of terms. So that's why he sometimes calls it splitting the atom of computation. You can think of it that way. When you look at his negation, it's clearly formulated in terms of the rewrite rules. Popping back up, that is the difference between the negation and session types, which is a linear negation and is related to the action of computation, and the negation from the Kairos types, which comes from the collection part.
Yeah.
And so what I wanted to do was to give a construction which allows me to have ladle give you both notions of types. So in order to do that, I need to talk about rewrite rules. I don't want to talk about every kind of rewrite rule. If you think now of TK as a carrier of dynamics, then if you have just like 0 arguments, then there's no interaction possible, right?
Yeah.
If you have 1 argument, there's a potential for interaction, but it's not until you get to binary term constructors, whether it's from the initial terms or from the lambda piece. It's not until you get binary that you start to get interaction.
Yeah.
And you can also prove that anything higher than binary can be faithfully encoded down to binary.
Yeah.
So you're only interested in binary because that gives you a notion of computation as interaction.
Mm-hmm.
Even if you focus on just interactive rewrite rules, that's still too rich to try to give an account like what we're trying to do. So what I was looking for was a further constraint on the rewrite rules. So I knew more about the rewrite rules, which would allow me to give the session type construction.
Yeah.
And the reflection reification thing turns out to give you everything you need. So I'll just give a sketch of that because this has been a very, very technical session. but I'll give kind of a high level sketch of what's going on, and maybe in another talk we can look at the details.
Cool.
If you understand how the tuple space works, then you can understand essentially what's going on. Not the Glertner style tuple space where you don't necessarily have reified access to continuations. But in the R space approach that we take with Rolang and RChain, essentially the idea is that at a name, you've only ever got either data or continuation, or the name is not being managed by the tuple space. And that is equivalent to the law of excluded middle. So this data integrity constraint on the storage is related to an observation that goes back 30 or 40 years, where people realized that you could encode excluded middle in terms of call CC. And the intuition is exactly what we see in the tuple space. It's like the idea that there's some data present at a name is a proposition about the data. That's sort of the name proposition of that data. And so then you can go and check if there's no data at that name, you freeze the computation that is the observer that's asking. And you make it to be a continuation.
Yeah.
And so then when data does get put at that name, that's the only time that the observer ever gets to pop out. So the observer will see either A or not A.
I remember you mentioning this at the RChain conference. It's a really cool idea.
Yeah, well, I mean, it's not mine. It goes back 30 or 40 years.
Yeah.
I'm trying to remember the researcher who observed it. I know that Ralph Loader explained it to me back in 91, I think. No, 92. And it was already old then. But I think I was the first person to actually use it as the foundation of a data integrity constraint for a data store.
Yeah. Interesting. So you're basically saying, like, if you're doing some computation, you have like an environment that you're doing the computation in, and if you need data at some name, if it's there, that's great. You take it and you proceed with the computation. But if it's not, you kind of just freeze it at that point, like take a snapshot of it or whatever.
You freeze the computation that wants it and put that at the name. That's right.
Yeah.
So
Cool.
now, if you look at the data type, we have everything we need to build that at the type level, right? So the lambda term that we've built here gives us everything we need.
In terms of the abstraction and application, you mean?
That's right. So everything is there to either have data, which would be a TKX,
Yeah.
or to have, well, in this case, the simplest way to do data is as names, right? Which is just a decoration of a TKX.
Yeah.
Either we're going to have data available or we're going to have continuations available.
Yeah.
The trick is that our type system is going to only allow for terms that balance placing data at names. It looks like a context-free language, right? So effectively, recognizing context-free languages, the only trick that context-free languages have above regular languages is that they can balance parentheses. That's the trick. We're effectively adding enough type machinery to make sure that in terms of this data abstraction thing going on, that they're balanced. So if you think of the data as open, or the abstraction as open paren, then the data is closed paren.
Yeah, that's nice.
Yeah, that makes sense.
But now we can do this at the type level, and so now I can give you session types. That's the essence of the construction. It's taken some time to get it clean. But the thing that I like about it, to widen the scope, is that I've made it really clear what the role of the derivative is here. When I made the first observations, I was just like, okay, well, now I know that I can use the derivative to get to this reflective closure gadget. And the question is, how do I articulate the fact that I've got a derivative related to evolution? Now I've sort of laid out all the steps for how that's done. I do want to point out that in the context of what we talked about last week, where we talked about knots, and I was talking about how I really feel that computation ought to start to be applied to the dynamics of physical systems, not in the sense of writing computer programs to implement Newtonian or, Lagrangian models of physical systems, but to use the fundamental principles of computation to elucidate principles of physical systems.
Mm-hmm.
That's like a big gap in the way we have been thinking about computation. I don't think there is an explicit program, so John Wheeler suggested that we ought to get it, i.e. physics, from bit, i.e. computation. So his whole program, it from bit. When he proposed it, first of all, computer science wasn't nearly as developed, right? Like Jean-Yves Girard was just contemplating linear logic. But this far down the road from there, we know a lot more about what's making computation tick and how it relates to logic and type theory. And then we're starting to see some of those ideas being employed in like a reformulation of quantum mechanics and things like that. So we know a lot more about it. And what I'm trying to suggest is, look, here we clearly have a notion of derivative that's clearly related to the evolution, the dynamics of the system. And so we're starting to get even the math of the notions of computation lining up with the way that math of physics has traditionally been carried out. And that's part of the motivation for me to give this kind of factorization and presentation so that we understand that, hey, this notion of derivatives is playing a foundational role in the evolution of the system, and we can explain exactly how the two are related. We can calculate and we can make predictions about how the derivative plays a role with respect to the evolution of the system. And I think that should take us a few steps further down the road in terms of being able to employ computation to the modeling of physical systems.
Do you think the derivative is an analog of something that is already known in physics?
Oh, yes. Yeah, I do. Exactly. And I think there's some category theorists who've been exploring very similar ideas, and maybe we could do an RCast about that. It's related to the management of resources and how the resources are being used in the formulation of dynamics.
Mm-hmm.
It's right there on the page, right? We can see exactly what it's doing. It's like it's taking a contributor to the dynamics and knocking one out. That's what the formal Leibnizian Newtonian derivative does, right? It takes a contributor and knocks it out.
Yeah, this is really interesting to me because, you know, in physics, the derivative seems like such a natural thing. I mean, you know, you have position and you take the derivative and now you have velocity, and you take the derivative and then now you have acceleration, and all of that seems very intuitive and straightforward. But it's very interesting that this same notion of derivative, at least, you know, the way you formulated it here in terms of a polynomial, is giving you a similar kind of notion, except for me at least, it's very difficult to think of like what is the analog of position and velocity in this case.
Yeah. And that's because in the standard way that physics is used to model dynamics, time is folded in.
Right.
Whereas here we've unfolded time, and time only happens when we do a reduction.
Yeah.
Right. So we've sort of done a further decomposition, right? And this is the very nugget that I'm trying to get to. Physics hasn't unfolded that bit, you know, and a lot of the formulations of relativity are attempting to unfold that bit, that and they get stuck, right? That's why you have this SpaceTime Gadget.
Yeah.
That's precisely the heart of the matter. But the thought is that if you refactor physics so that time isn't essentially a kind of coordinate, time arises from the dynamical evolution of things. Right? So the dynamical evolution happens because you're computing, and then we can get a notion of time that emerges from that, but not the other way around. It's essentially a repackaging of dynamics. There are some physicists who've argued for this. Julian Barber, who's kind of an outside physicist, but I think he's respected by at least Mullen and others. You know, they've talked about in his book, The End of Time, he talks about something like this. He tries to give a more intuitive account. Here, I'm trying to make some very concrete proposals for, you know, where the refactoring is, and this is what I've said over and over again. If you look at the way classical mathematics packages dynamics. Vector space just sits there. No dynamics happens until you have a function on it. Right? Whereas if you look at a process calculus or the lambda calculus or any of these notions of computation, it's the other way around. The algebraic gadget has the evolution together. Evolution and structure and function go together.
Yeah.
This is why it's really hard to give categorical accounts of computation, because all the category theory has been so heavily oriented towards the classical view where you decompose structure and function in this other way. You know, we just look at structure and then we use morphisms to encode dynamics. But the lambda calculus or the pi calculus or the rho calculus, the gadget is not well specified. You don't have a computational gadget until you also have the rewrite rules. And so if you're going to build a category, your notion of category would have to have morphisms that preserve the rewrites. When you have, you know, a rewrite system and you go to another rewrite system, you have to have a sense of what morphisms would preserve these rewrites. And that's a very difficult idea to get a hold of. Yeah. Christian, does that make any sense? Because I think you might be really interested in that.
Yeah, that makes sense. I mean, yeah, that's what this whole enrichment idea is about, is integrating the dynamics into the structure.
Yeah, exactly.